In a world plagued by idolatry and Hippocratic ideas of perfection, one is often left stranded attempting to discern what it truly means to be ideal. Especially if you're a gas. Today, we're going to be talking about pressure, temperature, phase diagrams. Hit the intro. Oh, that's right. I was too lazy to decide to make up an intro here. However, I wasn't too lazy to actually talk about phase diagrams today, so that's what we're going to hit ourselves off with. This is following along with my chemical engineering section of material and energy balances for the prompts 1A. I'll go ahead and flash those up on screen in just a moment, but this should be a pretty comprehensive video. I shouldn't say fully comprehensive, but it's going to cover a lot of components of how we can analyze a pressure temperature diagram and apply it to real world scenarios. I wore my chemical engineer shirt just for this, so let's do it. All right, so the first thing that I'd like to talk about when discussing a pressure temperature diagram is, well, what is a pressure temperature diagram? All right, let's do it. I think it is fairly intuitive, but you know, in case we're not there yet, let's get on the same page, you know? So let's see here. I'll go ahead and go and draw our diagram here. And it's going to be on your normal XY plane, yada yada, right? So on your Y-axis, you're going to have pressure, and we'll go ahead and label this in pascals. On your x-axis, we're going to have temperature. We'll put that in degrees Kelvin. Technically, this could also be degrees Celsius. You know, they're the same interval between each unit, right? And so, point being that we're working in SI units. Now, on this diagram, where we have pressure and temperature combinations determining what region will a substance be a particular state of matter, we will go ahead and label a couple points on here. I think the first one that's kind of important to mention is the triple point right here, where we have equal states of solid, liquid, and vapor regions. We'll talk about more about our triple point in just a moment. But let's also look up here at our critical point. I'll go ahead and even label him critical point. Now, the critical point is important because past the critical point in either the pressure or the temperature direction, we're going to have what is called superfluid, which is not super important for today's video. So let's not worry about going past our critical point. Remember I said down here, this is going to be called our triple point. And so then let's go ahead and connect these 2 points with a curve. And this curve is going to be where we spend most of this video. This curve is super important, and it is called our vapor. Sometimes there's a U in vapor, sometimes there's not. It doesn't particularly matter. I mean, unless you're British, in which case you always want that U. Vapor liquid equilibrium curve. What this means is that we're going to have, oh, I'm sorry, I'm kind of covering that up. Right, there it is, the vapor-liquid equilibrium curve. What that means is that at any pressure and temperature combination on that curve, so at any pressure, temperature combination on the curve, you're going to have a steady state equilibrium of your liquid and vapor phases. I'll go ahead and write that down because that's a fairly important concept. Steady state equilibrium. In an upper level thermodynamics course, we may actually define steady state and equilibrium as separate entities. However, today, steady state and equilibrium, I'm going to use them interchangeably to describe steady state equilibrium. The difference in steady state versus an equilibrium reaction is that a steady state is going to have constant proportions of reaction intermediates, whereas in equilibrium we're going to have constant proportions of reactants and products. For today's lesson, I don't think it pertinent to differentiate between the two, mainly because when I talk about steady state equilibrium, we're going to have constant proportions of reactants, intermediates, and products. So, that steady state equilibrium will occur between our vapor and our liquid. Vapor phase and liquid phase are going to count as, I guess you could say, our products and reactants. Perfect. So then let's go ahead and add a couple other regions to this graph. This will kind of be our sublimation curve, and this will be our freezing/melting curve. This could be more of a straight line, depending on which textbook you see it pictured in. I'll draw it more straight for our purposes there. All right, cool. So I'll go ahead and label our different regions of our graph here. This will be our solid region. Any pressure or temperature combination will result in a solid in there. This guy, oops. This guy here will be our liquid region, and down here we'll have our vapor region. Sometimes you may see a slight distinction over here and see a gas region, but we're also not going to worry about that, just because gases and vapors do represent sort of the same phase with everything we're going to talk about today. Also, we're not going to get to that high of temperatures, I don't believe. So, in moving on from this, this is actually a fairly good representation of a phase diagram. And I'm going to call this for water. We'll say this is for water. Phase diagrams are specific to their substance. And those substances also have to be pure in order for the phase diagram to apply. Now, and you're like, what is pure? I said they have to be pure for them to apply. Pure meaning, of course, that you're only going to have that substance in your sample. So now that we've talked about pure and we've talked about this phase diagram, we definitely want to be able to apply it. So how are we going to make a pure substance? So that kind of finishes up A1 there. And we're going to move on to A2. We'll call this A1, not the steak sauce. We'll go ahead and move on down here to A2, which is actually making a pure sample for our water. So in order to make a pure sample, let's go ahead and envision the container we would initially start out with, which could be something along the lines of a water bottle, right? And this isn't a great drawing because, you know, I'm not an arts major. I'm not even close. So let's say we have some water in here, water, and it's a liquid. And then we're also going to have air up here, which is a gas. And then in the water we'll probably have some dissolved oxygen, which makes a lot of sense. And our air is going to be composed of multiple different components like nitrogen and oxygen and water vapor, and all of those are going to add up to the partial pressures that really end up giving us air. Nitrogen being the strongest or most present component, therefore giving the highest proportion of its partial pressure to the partial pressure, to the total pressure of air, I'm sorry. Okay, so then in going from this, we have to go ahead and figure out how are we actually going to purify it. So there is actually a pretty good purification method for water in order to remove dissolved oxygen. And what we're going to do is we're going to attach kind of a vacuum pump to it. This is going to be my vacuum pump. Vacuum pump here. And then we can kind of light a fire underneath. These are flames. Look at those flames. Don't they look so flamey? Maybe it's on a hot plate or something like that. I don't know. And what this is going to do then is it's going to kind of distill the water. And this flame can't be too hot, otherwise we would kind of boil all of our water out. However, we can boil this, and because oxygen has a much lower boiling point than water, then oxygen is going to be removed by the vacuum pump, which is going to create a pressure gradient. Awesome. So now that we have this pure sample of water here, I'll go ahead and move on to A3. And what A3 is going to be is we're going to talk about how are we going to get our triple point from this now pure sample of water. Now, in this pure sample we have both liquid water and we have, in our pure sample of water now we have liquid water and we have water vapor. Liquid water, and we have water vapor. Awesome. And so then, in order to kind of transform this, what we are going to do then is all we have to do, we know that at the interface here, the interface is kind of the boundary between the two phases, and I call this the interphase. Awesome. And so what we're going to do here at our interphase, we know that there's actually an equilibrium taking place here between the gas and the liquid water. What we can do from that then is we can discern that all we have to do is really create some sort of solid substance. So in this container we're saying it's isolated from the outside world, therefore we can kind of create an internal pressure and temperature. So all we would really have to do for this container, we already have the liquid and the gas, all we would have to do, we know that at the interface, we know it's already on this line here, right? Because there is that liquid vapor equilibrium taking place, which means that the pressure is actually at the temperature, and the pressure match up with what's on this line. Now, this pressure in which we have a temperature on the equilibrium curve actually has a special name, and I'm going to go ahead and define that now. So that pressure is called, it's kind of denoted as Psat, and then our substance is water there. So this is the saturated vapor pressure. And all that means is that we have as much water as we can in basically our sample, and that this point here is saturated or has as much liquid and vapor present as possible. So in other words, it's in a steady state equilibrium. And so we denote the pressure that that's happening at is the saturated vapor pressure, or the Psat. Okay, so now that we know that it's on this curve at the Psat, we can kind of just bring the temperature down. And when I bring the temperature down, it's going to follow the ideal gas law, right? PV is equal to nRT. So if I decrease temperature, theoretically, the first thing on the other side, now that we have this stagnant volume in here, I said we have that container and it's closed, the volume can't decrease, so therefore the pressure must decrease at this interface here. And what's actually going to happen is you're going to have solid ice start to form at this interface. Tiny little ice chunks. And to do that, all you have to do is reduce this temperature in some sort of fashion. And it's just going to move right down this curve to the triple point. and therefore we're obtaining our solution. Isn't that interesting? Something that probably hasn't really happened to you that often, but it is something that we can actually do, is have solid, liquid, and gaseous water all at the same time. Now, the uses for this aren't, something that we're going to find application for all of the time in, the average person's life, which is why we don't really talk about it that much. But isn't it still kind of cool that we can make that happen? I don't know. I think it is. So with that, we're going to bring us on to A4. And A4 is kind of a sample scenario here. So A4 says, starting from a sample of pure water at 80 degrees Celsius, what is the maximum pressure that this sample can be at in a container with a movable boundary? Draw how the sample looks at increasing pressures until it is all liquid and at a pressure above the saturation vapor pressure at 80 degrees Celsius. So, as in any physics problem, it's pertinent to write down the initial conditions. And I think that the initial conditions are pretty straightforward here. The initial temperature is 80 degrees Celsius. We also have an isolated system, which is our container here. All right. And then on top of that, we have this movable boundary here, right? So let's kind of draw a little picture for our system here. So here, I'll go ahead and draw this out. We'll make it brown, because I haven't used brown yet. Isn't that kind of interesting? I don't know. Ooh, brown's kind of a gross color. Never mind. I'm sorry. So there's our brown container. And I'll do a gray movable boundary here. That way it's kind of differentiated from the rest of it. And I think the easiest example, or the one that at least comes up the most in most people's minds of a movable boundary, is indeed a piston. So this is a piston. All right. And so that takes care of our movable boundary and our system, and I can just denote that the temperature is at 80 degrees Celsius here. Now, we were also told that this was all water vapor. All water vapor, which means that the water vapor is going to have a volume associated with it. The same is true for the triple point, right? At the triple point, the actual temperature of water is a little bit above freezing at 0.01 degrees Celsius. This is what the temperature is going to drop to once we reach our triple point, which makes our pressure equal to something around 611 pascals. Note, I think what's most interesting about this triple point is that the temperature itself is not actually at the freezing point, even though on our pressure temperature diagram, you can see that it's on this line, and so we can assume that kind of at 1 atmosphere has to be somewhere around here, right? And this would be our normal freezing point. So here would be about 1 atmosphere, which means that the pressure is going to be less than 1 atmosphere. 1 atmosphere is equal to 101,325 pascals. And this is true. The pressure is much lower than 1 atmosphere. Okay, and this is the, so we're going to look for that pressure that matches up with 80 degrees Celsius. We want to know what is the maximum pressure that this sample can be at. So I'll call this P max here. What is the maximum pressure that this sample can be at? So let's look at our phase diagram to kind of figure this out. we know we have water vapor, right? So the max pressure, we can see that there is a very clear max line for our vapor. Let's see if I can pick any color here. Okay. So there should be, any time in this vapor region, there's a very clear max. And where is that max? It's on the vapor-liquid equilibrium curve, right? Which means the max pressure is equal to the saturation vapor pressure. Okay? And that is, again, that makes sense because it's all gas. The max pressure is going to be the same as the time when it's starting to change into water. Okay, so then there is actually a tabulated value for this. I believe it's somewhere around 47,414 pascals. I know it's in the 47,000 range. I don't know the exact number off the top of my head, but I think that is about the general gist of the way it is going to be. So you can also see that this max pressure here is less than the 1 atmosphere, which also makes sense because the max pressure that it would be at that 101,325 Pascal number, or 1 atmosphere, is going to be 100 degrees Celsius, or the boiling point of water, right? So again, this number does check out. So let's say I start to move this boundary. Okay, and in moving this boundary, oh boy, what I have, I'm going to bring it down a little bit. And so what is actually going to happen when I move this boundary? Well, obviously the volume of the gas is going to decrease, right? So we can say when I come over here, the volume will decrease of the gas. So the volume will decrease. Well, it's a low pressure initially, right? It's even lower than 1 atmosphere, so the air will follow the ideal gas law. The ideal gas law says PV is equal to nRT. R is a constant, so R can't change. Okay, so we're decreasing our volume here. If this is going down, oh, there it is. If the volume is decreasing, something else has to decrease in order to balance out the equation, right? Okay. So that logic kind of follows out. The pressure, let's see, is the pressure going to decrease? Your initial thought would be yes, because that's a piston pushing down on it. Of course the pressure is going to decrease. The true answer is no, and I'm going to show you why. So the pressure actually stays relatively constant. The reason being that if I push this down, I'm actually going to get liquid water forming at the bottom here. Isn't that different? See, that's kind of neat. So I have less gas, less volume, and now I have liquid water. So if the pressure is staying the same and this is staying the same, something has to change. Actually, both are going to change. The number of moles is going to actually decrease. And you're like, why? The number of moles in the container should stay the same. Nothing is escaping out the sides, right? And no, nothing's escaping out of the sides of the container. Everything is still in there. But what you're doing is you're phase transitioning from a gas to a liquid. A liquid's not going to follow the ideal gas law, right? So therefore the amount of moles has to decrease. The temperature is also going to decrease. Assuming that this is not an isothermal system, which wasn't given in the source material either. Temperature is also going to decrease to kind of counteract this. The reason being, if we look at our phase diagram up here, to go from a vapor to a liquid, I'll go green here, to go from a vapor to a liquid at a constant pressure, I have to decrease my temperature. We don't often think about this in the daily life. We think about if I'm going from, liquid water to a gas, that I'm going to have to add heat to evaporate it or boil it, right? But it actually gives off heat to its surroundings in order to condense it, which is something that isn't generally thought about. Okay. I'm going to go ahead and draw our final scenario here, which is at some point this piston is going to go low enough that actually the volume will kind of zero out and you'll be left with only this liquid water. Isn't that fascinating? And that's kind of one of the foundational concepts of chemical engineering. Kind of all of this boils down to how did we use our phase diagram to actually show something in real life existing. Thanks for coming with me on this journey. I'll see you in the next one.